It was very tutorial, probably stuff that, most of it was stuff that you knew previously. This one is really going to be a grab bag of a whole lot of research work that research and development work that we've done in microwave photonics, using some of the concepts that I've outlined in the previous talk. So a selection of microphotonic examples, and the general topics are an electronic warfare photonic link and down conversion system. And this is some work that we did up to 10 years ago, and over perhaps up to about 5 years ago, so from about 10 to about 5 years ago, with DSGO, BAE systems, and then Photonics defense systems. I'll talk a little bit about phase shifting and transversal filtering, more as a conceptual notion of what you can do with a few results. Then I'll talk in a bit more detail about photonic frequency measurement. Photonic frequency measurement is essentially something that we've done quite a lot of within Kudos, so you'll notice I've changed my slide template and a little thing on the bottom there. So this is leading up to some work that we're doing currently with Kudos, so we'll eventually talk about some linear optics, and we'll hopefully get into some familiar territory. Okay, so where we started maybe 10 years ago with DSGO, maybe even longer, is trying to develop the technology in Australia to be able to design and fabricate our own high-speed electro-optic modulators. And these were done on the material lithium niobate. Of course, these are sort of fairly ubiquitous now. But the key to being able to make these is actually get these electrode structures. And you can see here that they're quite extraordinary. There's about 30 microns of gap here between the two ground planes. This is like a coplanar waveguide structure. And in the middle, you've got this electrode that's about 5 microns wide, about 40 microns tall, and about 2 centimeters long. So you've actually got to have this skyscraper of metal running down the length of a modulator. And I believe that you'll see something not too dissimilar like to that in commercial modulators today. Not your 10 gigahertz ones, your 40 gigahertz ones will have something like that in them. And that's one of the reasons why they're very expensive, because it's very hard to actually sort of maintain this sort of thing. And it's also a reason why I think that sort of 10 gigahertz is much more palatable, because the aspect ratios here tend to get a bit better. Once you get up above about 40 gigahertz, then you've got all sorts of issues with packaging and trying to stop the box and the chip itself actually resonating with the RF frequency. But up to 40 gigahertz, it's all fairly plain sailing. It's just making this electrode very, very tall, very thin. So there's a lot of micro engineering in terms of actually being able to make that, and so that's what we invested a lot of our time in. We also invested a lot of our time, perhaps foolishly, in packaging these. And here you can see a package modulator. This is an old generation package. We made some slightly more compact ones. But we packaged them and actually got them validated up to military specifications and flight trials. So they were shaped and baked and actually met military specifications. You can see here this was actually packaged with an amplifier in front of it, which is probably also not a particularly sensible thing to do, but that's actually one of our modulators. And we still use our modulators in our lab today. We've got about 20 or 30 of them still left over. They were licensed to an Australian company to manufacture, but of course the aerospace do a very good job of manufacturing things, so that's where we want new ones, that's where we buy them from. We don't make them. So please don't ask me to make you modulators. Unless they're incredibly exotic. All made out of silicon. Okay, so that's some of the work we did was working on modulators, and once we'd made our modulators, we wanted to demonstrate them sort of in a realistic electronic warfare environment and sort of do some research with them in microwave photonics. And really that's sort of where the microwave photonics group at RMIT sort of grew from the integrated optics group. So the integrated optics group sort of developed the modulators, and then the microwave photonics group was trying to do stuff with them. So a simple example of something that we did with them was basically actually implement this 4 antenna remoting system feeding back to a base station. And this base station is actually sort of a black box unit that we had to get shared with us as a sort of military secret from the USA. So a lot of the challenge was actually making our stuff actually plug into their system without knowing what was inside and just show that it all worked. So there was a lot of effort in trying to essentially make these things so that you could flight trial them, and actually, well, a lot of the effort was getting the black box from America, and then once we had it, actually sort of interfacing to it. So the technical challenge was really to have 4 antenna clusters. So you can see here are the antenna clusters, and essentially they're looking in different directions, spaced by about 30 meters, going into this black box. And the idea was to demonstrate that the photonic link did a better job than the existing RF links, up to 40 gigahertz. We did succeed in doing that, particularly from 20 to 40 gigahertz. It's very, very hard to get competitive with photonics from 20 to 40 gigahertz. Up to 20 gigahertz is actually some pretty good solutions in the RF domain. So then we thought we'd go one step further, and this is sort of starting to push into a project that was called SIDARN. The previous project was called Project Arrangement 10, cryptically named Project Arrangement 10. This one's called SIDARN, which is an acronym that stands for something, but it's not important what it stands for. So what that was meant to do was really look at, okay, like I said, we've done this photonic remoting, we've actually got all this stuff in fibre, let's do something a little bit interesting with it rather than just, you know, having it as a pipe that goes from an antenna to a detector and then goes in, all the interesting stuff goes on in the electronic world. So here's a couple of examples of things that we did with this. You know, not particularly earth-shatteringly innovative, but it's sort of illustrative of the sort of things that you can do. So you've got 4 antennas, the 4 antennas on the corners of the aircraft, and essentially just wavelength division multiplexing them all together. So different wavelengths, muxing them together, amplifying them all together, modulating them now with a local oscillator. So what the receiver here wants to receive is something at sort of the order of about 2 gigahertz rather than the stuff coming in potentially at 40 gigahertz. So what we want to do is modulate it with a local oscillator that will mix this high frequency signal. Say this is 20 gigahertz, it'll mix the 20 gigahertz band down to something like 2 gigahertz. And then feed that into the radar warning receiver. And so the idea was to demonstrate that you could get an improvement in weight and cabling complexity by sort of multiplexing all these things together, and particularly that you could have essentially one modulator and one local oscillator here to actually do that mixing down at the central processing unit. The inverse of this, we also tried, is basically to have 4 wavelengths all going through the same modulator attached to a local oscillator signal, and then basically demux them into different channels here. So you can have 4 RF channels that you're mixing with the one signal that you're receiving. So this is essentially just the inverse of that. So this works just as well. There's nothing particularly challenging about it, apart from sort of really the comparison between, okay, how does this compare to an RF mixer? And I can tell you now, RF mixers at 40 gigahertz are horrible, absolutely horrible. 20 gigahertz, they're good, but at 40 gigahertz, they're horrific. So if you want to mix things up above 20 gigahertz, Photonics is the way to do it. And this is actually a picture of it. So this is the system that we put together. It's actually got our modulators in it, so you can sort of get an idea of the size. So this is the sort of rank. A lot of that is temperature stabilization and vibration stabilization and things to make it so that, you know, when you shake and bake it, they actually had recordings of a machine gun fire that they would put on their shaking system to see whether the system could actually withstand essentially being attached to a machine gun. And it did. So that's the system that we put together. So we did a lot of that sort of development, had a lot of insight into, okay, this sort of stuff is sort of practical in those sorts of environments, and this sort of stuff isn't. So that's interesting and historical. Okay, so something slightly more interesting. when coming out of that exercise, we thought, look, you can probably do even more interesting things than just simply mixing up and mixing down. We know that from communications. Can we do things like phase shifting and filtering? People have known that you can do sort of filtering with RF signals with photonics in the RF domain already, but we did some sort of interesting work, we think, in the photonic phase shifting. So the simplest version of this, and this is really illustrative, is to take an RF signal in, modulate it, split it in half, and delay one by a time delay, and then add them back together again. So mathematically, this is what I've done here. I basically said, okay, I've got a time delay here of 1, so this is in phase, and some other time delay here, delta t, and this is the RF frequency. So the phase that the RF signal gets going through there will be the frequency times the time delay, then add them together, and what I end up with is something that's like a cosine of that term there. So I get a cosine that varies with frequency and is adjustable with the time delay. And so here's a picture of this with a linear RF power here versus frequency. And this is a sort of a crude filter. So you can see that basically, it passes the low frequencies here. If you get it just right, the amplitudes and the phases here, then you can actually get a really deep null here where no RF signal is passed here and then come back up again. And this technique is what's called a two-tap transversal filter, and it's often used for knocking out jammers. So if you could adjust this time delay, you can tune this so that null coincides with a jamming signal that might come in. Okay, so how would you implement it? Here's an example of how we implemented it. Basically, we took 2 laser diodes, so one at wavelength lambda 1, one at wavelength lambda 2, summed them together, and then modulated them both with the same RF frequency, and then used a piece of, we've done this in a number of ways, and I'll show you a different way later, but in this particular example, we used just a piece of single wave fibre, a long length of single wave fibre, and just used the dispersion between these 2 wavelengths to accumulate a time difference in the RF domain. So basically, something like a pi phase shift between something like a 5 to 6 gigabit signal. Sort of 10 to 20, 30 kilometres of single wave fibres will do. Then pick that up on a photodetector and look at the RF output. So what we saw here is this is actually a picture from a optical spectrum analyzer, and what we've done is replace the wavelength range here with the time delay in picoseconds that you would actually see if you put it through that piece of dispersive fibre. So I've replaced this axis here from wavelength, it's actually measured as wavelength, with time. So I'm saying this is 0 time, this is 196 picoseconds. And so that's what I'm picking up with my photodetector. I modulate those with my RF signal, and then I receive that with the photodetector, and this is the response that I see now on a dB scale. And what you can see is the modelling here, this is the blue line, is modelling, predicts all these nulls, and sure enough, the measured signal matches it. So you can see here that you get quite deep nulls, about 30 dB. Getting these really, really deep is a challenge, but it means you've got to get the powers and shapes of these 2 taps to be exactly equal. This is quite good for a notch filter. So you can see very, very, very simple proof of principle. Okay, but I'd like to do something a bit more interesting than that. So a two-tap filter basically just gives me a sinusoidal response. Most filters aren't sinusoidal. They've got Chebyshev responses, or at the very least a flat top. That's really what I want for my filter, for a passband filter, for example. So how do I do that? How do I make a passband filter? So this is in the frequency domain. What it turns out is that the dispersion in the optical fibre is actually performing a Fourier transform function. So it's taking my time domain pattern and converting it into an RF frequency domain by essentially, literally doing a Fourier transform on it. So if I want this top hat function in the frequency domain, what that says I need in the time domain is this sinc function, so sin x on x. And ideally I'd like that to go on for infinity in both directions, and I'd like all this to be continuous, but I can't do that. So what I do instead is I sample it. So I have two samples here in this primary lobe, and then I put some extra. So this is actually exactly what I just showed you. If I just had those two samples, it was constrained to that degree, it would be a sinusoid. If I add these other two samples here, so have another two wavelength channels that are separated in time or wavelength, depending if you've got linear dispersion here, then I need these two other things, but they need to be negative. They need to have the opposite sign of the RF modulation. There's no such thing as negative optical power. They have to have, if this is being modulated with a positive RF signal, this one has to have a negative RF signal on it. So the question is, how can I do that at the beginning? How can I condition my signal in such a way that I have these modulated with a positive gain and these modulated with a negative gain? So this is where the Mach-Zehnder nonlinearity actually helps you. So remember, the response of the Mach-Zehnder is actually a sinusoid, so cosine in fact. So I can naturally, without any bias voltage, I'm biased up here. So if I put a RF signal in, it would actually oscillate back and forth, and I'd just get the second harmonic as it oscillated back and forth from here. If I put a DC bias on to take me to quadrature, now I'm at the high gain linear region, which is really where I want to operate. But I can also put a bias of minus V pi onto and take me to this point. And that means if I've got the same signal going in here, I'll have the complement of this signal here, so I'll actually achieve a negative modulation. So I've got a choice with the Mach-Zehnder of biasing with a forward bias or biasing with a negative bias, and that allows me to have a positive or a negative gain on these RF signals. So that's an opportunity to sort of implement these more sophisticated filters. So how would we do that? Here's an example. There are simpler ways of doing this, but this is probably the most illustrative way of doing it. I have 4 wavelengths, and I have 2 of those wavelengths, and I've called them lambda 2 and lambda 3 here, go into my first Mach-Zehnder that's biased with positive quadrature. And so this is essentially what I just showed you previously. So this is the 2-tap transversal filter that would give you a sinusoid. I then have another Mach-Zehnder with 2 other laser diodes with now lambda 1 and lambda 4. So these are on either side of these 2. And they're going to a Mach-Zehnder that's been biased with a negative bias. So the gain on this is negative. I can adjust the power coming out of these laser diodes to give me the amplitude of those, and adjust the bias here to give me a sign. So I can now dial up a real time domain function with negative coefficients here. I put all of those through this dispersion element, and then pick it up on a photodetector and look at the RF output. And this is what I see. So this is again a reading from a spectrum analyzer. However, I've cheated a little bit and I've inverted those two just to illustrate that those have been modulated with a negative RF signal. So this is actually illustrative, but so I've just inverted from here to here to show you that it's actually negative modulated. And I picked that up with a photodetector, and this is what I see. So the model says that I should see this sinusoidal response, but what's happened is I've actually got a flatter top than I had before. Now, if I wanted an even flatter top, if I want to really make this flat, make this sharp and square, I need to keep adding more and more and more of these, and I can make that flatter and squarer. But this just sort of illustrates that you can actually do that. Okay, more sophisticated again. For a lot of applications, and I'll actually give you an example of an application where this is important at the end, I'd like a 90-degree phase shift. I said before that optics is good for giving you a true time delay phase shift. This is a phase shift where it's basically a length and it scales linearly with frequency. So basically the phase scales linearly with frequency. Zero frequency, zero phase. At one frequency, 1 unit of phase, two units of frequency, 2 units of phase. So it scales linearly with phase. There's a lot of applications where I just want to have a 90-degree phase shift for all frequencies. So this is zero frequency, and I want to have basically plus J, 90-degree phase shift for all positive frequencies, and minus J for all negative frequencies. Instances where I want to do this is where I want to, for example, combine arms from spiral antennas so that each physical quadrant of that spiral antenna, if it's got 4 arms, has the appropriate phase shift for all frequencies. Spiral antennas can operate at sort of 2 to 20 gigahertz. That's an example of where I would 90-degree phase shift. There's a lot of other signal processing applications where you want this. So the opportunity here is basically, okay, if you dial up this sort of frequency response, so you basically have, instead of using, putting these two through the positive modulator and these two through the negative modulator, I can put these two through the positive modulator and these two through the negative modulator. I can get that response, and we've demonstrated that that works as well. So there's opportunities for, and you can use the same system, you're just changing the bias voltage on the modulator, and you can potentially change that at nanosecond frequencies. So you can adjust this from being a flat top response to a 90-degree phase shifter to whatever, very, very, very quickly. And we've used that to demonstrate, for example, with that spiral antenna, being able to change the beam pattern very rapidly and scan the beam over different spatial domains. Okay, so now frequency measurement. And I may end up finishing up a little early, which might get us back on track. We've got another 10 slides. I'll just talk about frequency measurement again in the context of electronic warfare, and this is now getting closer to the sort of work that we're doing in PUDOS. The idea with electronic warfare is that you want to continuously detect all potential threats. So you want to always be watching in all directions, at all frequencies, for all possible threats, which is challenging. The most precise way of doing that is with a scanning receiver. You take a very, very narrow oscillator and you scan that over a mixer through your signal and basically look at the response that comes out. That's essentially how a spectrum analyzer works, an RF spectrum analyzer or an RF network analyzer works. So they're very, very precise, identify threats very, very accurately, but they're slow and they're serial. So it's got to scan. The frequency's got to scan, and the narrower your line width is, the slower that thing's got to scan. It's just a fundamental limitation. And they're serial. While it's looking here, it's not looking over there. You can have more and more and more of them, but essentially you're always going to miss something. And there's this concept of probability of intercept, so the chance that you're going to see a threat out there. And you want to increase that and make that as high as possible. So the other thing is that, I mean, a lot of systems do use scanning receivers, and the assumption is that you have a sort of a scan frequency, and some of the threats out there know what the scan frequencies of the scanning receivers are, and so also scan behind your scanner and can actually hide from the scanner in that way. So there's lots of reasons for not wanting to actually have a scanning receiver. So this is where the concept of instantaneous frequency measurement comes in, and we can have a big debate about what instantaneous actually means. What I actually mean is something like 100 RF wavelengths. So by optical standards, incredibly slow. So instantaneous means that, okay, at any point in time, once I've measured 100 RF wavelengths, I can tell you what the frequency is. So considering RF wavelength, RF frequencies are sort of the order of 2 to 40 gigahertz, that's actually pretty slow. But by scanning receivers standards, that's actually quite fast. So The advantage of instantaneous frequency measurements, and I'll tell you what this is in a moment, you can always watch everything. It's simultaneous and it's in real time. So it's always giving you a measurement of everything. But it's crude. It's really crude. It doesn't have anything like the accuracy or precision of this sort of system. And so it can't be used to accurately identify threats, but it's a good early warning system. So basically it's always watching, and it can always say, hey, maybe there's something over there, can you point your scanning resources over there and check? So you're unlikely to miss anything, you just don't know what it is. That's sort of the point of this. So effective electronic workspace systems need both, and that's the key. You need to have this crude instantaneous frequency measurement system to tell the sophisticated system what to do, where to look, where to put all your computational resources or put your signal processing resources, where to tune your oscillators to. Okay, so you see this picture before. Basically, the simplest IFM and this instantaneous frequency measurement system out there is just an interferometer. It's just a filter. This is basically, you have a RF input signal, you split it by 3 dB, you put a known time delay on here, you add them back together again, and what you see here is that the output RF power oscillates with frequency. So in this range, from here to say here, I can map a particular output RF power to a particular frequency, and I can use a lookup table and say, okay, well, this is what that power should correspond to, so I can tell you what the frequency is. So that's really a very, very simple frequency measurement system. It's simple. It has passive components, so RF power splitter, passive, time delay, passive, summation, passive. There's no electronics per se here. This is could all be done with just waveguides. So it's very, very simple, but it has high frequency output. If I've got a 40 gigahertz signal in here, I get a 40 gigahertz signal out there, and I have to measure the 40 gigahertz signal independent of the other signals in order to be able to see what's going on. I need to be able to have a broadband detector out here. So this is a problem. Broadband detectors can be expensive in the microwave domain and the optical domain. So it's got high frequency output, and that's tough. There's an alternative. I can do the same thing, and this is basically a multiplication IFM, or essentially autocorrelation. What I can do here is I can split the signal, time delay, instead of adding them, I can multiply them. So if I've got 40 gigahertz here and I multiply it with 40 gigahertz here, I can low pass filter the output, and the output I'll essentially get a DC voltage, and that DC voltage should vary in an oscillatory way with the frequency because of this time delay between those two signals. So when they're in phase, you'll get a strong signal, and when they're out of phase, you'll get a weak signal when they multiply together. So this is good. Low frequency output, simple receiver. Okay, so I can just have a voltmeter here. That's easy. The problem is now I've got an active device for RF mixing, so I need to have this mixer here. And particularly, as I mentioned before, at 40 gigahertz, this is really, really difficult to do. They're broadband, they're expensive, they're delicate. So you do, and this IFM, you want at the fringe. You don't want that in your central processing unit. You want that where the signal is freshest, because that's really you're relying on that to catch everything. So it's got to be right out there with the antenna. So you don't want to be putting this delicate mixer out there for reasons that I said before. Okay, so there are photonic suggestions. So there are different options for doing microwave photonics. Most of these are this summation version. So basically what you have, for example, this is a version that was done by Lynn Wynn and Dave Hunter at DSTO. It's basically you have two laser diodes, WDM them together, electro-optic modulator, modulate them, dispersive medium looking familiar, then basically separate them out and measure them with two photodetectors. And what you're relying on is basically, again, this sort of time delay incurred by this dispersive medium to cause the signals to essentially accumulate a phase delay. So it's basically the signal fading, you're measuring with a photodetector, and then you're comparing the signal fading for the two different waves. Problem is that you need to have, again, high-frequency photodetectors, 2 of them, and as I mentioned before, high-frequency photodetectors are sort of failure-prone and expensive, and they've got low power handling capacity. Here's another example. This is a very similar concept. However, here they're using amplitude modulation and phase modulation, and then picking those up with looking at the differences between the dispersion of those two, picking up the photodetector and doing some signal processing on it again. Again, you need broadband photodetectors in order to be able to pick those two signals up. So, got lots of broadband passive devices. The delays here, excellent. Don't have a lot of attenuation. Combiners, WDM combiners, WDM splitters, all those sorts of things, really good in fibre optics. Essentially no bandwidth limitations for the microphotonics. So that's really good. The difficulty here is that you still need broadband photodetectors. So that's a limitation of these systems and really deploying them. We'd really like to use cheap and nasty photodetectors. So we came up with this concept based loosely on the mixing system that I showed you initially that we did under SIDAR, where we modulated the RF signal onto one modulator from a splitter, and then basically took the other half of that signal, delayed it with a coaxial cable, and put it into another modulator and remodulated the signal. So essentially mixed it up to whatever frequency, and then mixed it back down to DC. And then you can pick that up with a DC photodetector. And so we managed to actually achieve the frequency measurement that we were looking for. So you can see there's this sort of oscillatory behaviour here. We calibrated the link gain of these modulators, and a significant issue here is the link gain of this modulator with all this RF cable in front of it. And came up with this modelled response, and then all these spot frequencies are measurements that we actually made at the digital voltmeter. So you can see there's a really good match between the measurement and sort of calibrated model. But what you can see clearly here is that the oscillations are damping really quickly as you go up to high frequency. So if you wanted to use this for frequency measurement, you could use it in this range, so from this peak to that null. And what we did was we took those points and basically mapped them back to frequency and plotted them here. So this is input frequency versus output frequency, and you can see that there's relatively good agreement here. So this is an okay proof of concept, but the inclusion of this RF cable really isn't practical. We really want to get rid of that. So what we thought was that maybe we could use all-optical mixing. Maybe this was a good opportunity to explore the use, instead of using electro-optic mixing here, use all-optical mixing.
We have a little bit behind the schedule, so the cameras speed up a little bit.
Okay, so 10 minutes over.
Yeah.
Okay, I'll see that. So here's the microphotonic mixing. Basically, what you can see here is there's a laser diode, carrier, modulated. This is just to demonstrate that you can do analog mixing with polynomial fiber using four-way mixing. And we have, so this is what we're using to carry our signal. This is the carrier that we're using as a pump. And what we hope to do is mix those two together and produce some mixing products. So here's the two carriers. We modulate one of those carriers with a signal. We amplify them through this amplifier, put them through a highly nonlinear fiber, and it'll create these idlers through four-way mixing. And the idlers will have the RF signal on them. So that's what we see here. And what we hope is that that idler will actually be a really nice match to the RF signal that came in. So we did this experiment. We've got the modulation here. We've got a cascaded fibre break grating here. So basically, this is a grating. Instead of a dispersive fibre, we've got two gratings essentially with a known delay in between them. And so this grating reflects lambda 2. This grating reflects lambda 1. So basically, you get a fixed time delay between the two carriers here. Amplify them, plug in on your fibre, and comes comes out here. This is what we see in the optical spectrum analyzer. So you can see this was where we put the signal in. This is cross-phase modulation. These are your idlers, and you can see that there's an RF signal on your two idlers. So what we did was we isolated out one of the idlers and measured the response. So what you can see here is that we measured the response at lambda 1, which was one of our input response, and this is just your typical microwave photonic link response. So that's what we saw through here, typical microwave photonic link response. And then we measured at one of the idler frequencies, and that's what we got here. So the mixing gain is we're losing a little bit of power because the nonlinear mixing is not particularly efficient. But what you can see is that it faithfully reproduces the RF signal. So we're getting a very, very similar response to the RF signal, just offset by the link gain. And the link gain matches what we measured for what we expected for the link gain of this nonlinear fiber with the powers we were using. Okay, so what we proved then was you can use the highly linear fiber for mixing analog RF signals. And so what we did was now implement the frequency measurement system. And so we took laser diode 1, laser diode 2, multiplied them with a RF signal, put them through the cascaded fiber rate grading to get a time delay, amplified them. So two carriers. This one's modulated. This one's modulated. Delayed one of them, so this one's now got a delay on it. This one doesn't. And then put them through the highly linear fiber. And what I'm doing here is I'm considering the nonlinear generation of these idlers separately. So I have the idlers produced with this signal and the idlers produced with this signal. So this one has a phase shift on it, and then add them together. And it turns out from mathematics that this is allowable. And so then look at the idler, and what I have is actually the original signal plus a time delayed version of it. What I expected to get was a multiplication of those two. What I actually got was a superposition. And so if you follow through the maths of this, it's interesting to see that actually the output, if you look at this, is actually the superposition of those two. And so here's the modelled response, and this is the green line, and then the measured response. And what you can see is there's very, very good agreement between the modelled and measured responses of the system. You can also see that we're now going up to 40 gigahertz, and we still have a reasonable level of oscillation. So we aren't suffering from the RF attenuation loss that we had with the double modulator version of this. So this actually works up to 40 gigahertz. The difference between this one is basically that this one has wavelengths at these two things, so a particular delay. And what we've done here is we've changed the wavelengths so that the time delay, there's actually another gradient further on down here, is longer, so that the longer time delay gives us a shorter period of the ripple. Now the key point here is that this is incredibly stable. You can go away, come back tomorrow, and it's still working the same way. But what you've actually got here is a coherent superposition of two optical carriers from the idlers. And through the nonlinear process, you're actually multiplying the phase of the two carriers together. So it doesn't matter what the absolute phase of the two carriers are going into that highly linear fiber, you get the same phase coming out. So even though you're getting the coherent superposition of the RF frequency, you don't get coherent superposition of coherent interference and noise from the coherent superposition of the carriers. Here's essentially inverting that model's response and putting those measurements in to get a frequency measurement. Again, you can see that the response is pretty good. The errors generally turn up as band edges, as you'd expect, because of the sinusoidal response. So, conclusion. Demonstrated microwave photonic promoting. Demonstrated microwave photonic mixing in parallel with the sidearm project. Demonstrated microwave photonic filtering using 2 taps and 4 taps with positive and negative coefficients. Demonstrated microwave photonic frequency measurement, and also microwave photonic frequency measurement using all-optical mixing. And what we're working towards is the opportunity to do more complex systems with multiple IFMs in parallel implemented using, this was implemented using polynomial fiber. By integrating on a chip, we should be able to do more things in parallel. Thanks.
We have one or two quick questions before we go to lunch. Everybody's agreed, I guess. All right. One quick question. The dispersion, like using two lasers in dispersion, isn't that the same thing as just doing the interferometer? Like, could we do the same thing, just building a fiber?
Using a physical delay.
Yeah.
Yes, but you'd need to worry about coherent interference. You'd have to keep those two lines very stable. So essentially, yes.
Okay, let's thank Arnan again.
So I have a very quick announcement that